Here's a little survival trivia question for you to ponder. We all know that rubber is naturally a fantastic insulator, right? It stops electricity dead in its tracks. So why in the world do aeronautical engineers intentionally manufacture airplane tires to be slightly conductive?
To really understand this invisible electrical pressure, let's start with a force you already know intimately: gravity. To get a grip on this, think about how pushing a charged particle into an electric field is literally the exact same thing as pushing a huge boulder up a really steep hill. Both gravity and the electrostatic force, which physicists call the Coulomb force, follow the exact same mathematical rules. They both weaken the further away you get from them, which is known as an inverse square dependence. Honestly, the only real difference here: gravity deals with heavy, massive objects, while the Coulomb force deals with tiny little electric charges. And here's the absolute coolest part about both of those forces. Your physical effort doesn't just disappear. When you push that boulder up a hill, you're doing work against gravity, right? And that work is banked. It is literally stored as potential energy. Let the boulder go, and it rolls right back down, converting that stored energy into motion. The exact same thing happens when you force two positive electric charges together. They naturally want to push apart, but if you force them together anyway, you're storing up electrical potential energy. Because both of these are what we call conservative forces, all that energy is perfectly preserved. Moving on to, what is electrostatic potential? Let's take that boulder on a hill idea and bring it directly into the world of electricity.
Alessandro Volta. He was the brilliant Italian physicist who actually developed the very first battery. And ultimately, he's the guy who gave a very recognizable human name to this super abstract concept of electrical elevation. So the big takeaway here is that what we colloquially call a volt is at its core just a measurement of work. It's simply the amount of physical work required by some external force to move a single standard unit of charge from infinitely far away, where the potential is basically zero, right up to a specific point on our invisible map. Think about it. When you buy a standard 9-volt battery, that label is literally telling you the exact height of the electrical hill it's capable of pushing charges up. Pretty cool, right?
Storing sparks, the capacitor. If we know how to create this electrical pressure, this voltage, how do we build a bucket to actually catch and store it for when we need a huge, sudden burst of energy?
This is a tiny device that acts exactly like an electrical storage tank. If a battery is a continuous pump, a capacitor is the giant water tower sitting right above your town. And honestly, the most mind-blowing part about a capacitor? The energy isn't actually stored in the metal plates themselves. It's literally trapped in the empty, invisible space, the electric field between those plates. Crazy, right?
Now, you might hear the word capacitance tossed around in a physics class. Please don't let the math terminology scare you. Capacitance is simply measuring the physical size of your storage tank. A small cup fills up super fast, but obviously holds a lot less water. That's low capacitance. A huge industrial tank takes way longer to fill, but it stores massive amounts of water. That's high capacitance. It's literally just volume.
But there is a massive physical limitation here. Get ready for a pretty wild fact. If you wanted to build a parallel plate capacitor that held just 1 farad, which is the standard unit of capacitance, and you just used an empty vacuum between plates spaced 1 centimeter apart, your metal plates would each need to be 30 kilometers long and 30 kilometers wide. To put that in perspective, that's an entire major city, just to hold 1 farad of charge. Crazy, right? Boosting power with dielectrics. Since a 30-kilometer wide plate is definitely not going to fit inside your smartphone, physicists had to come up with a brilliantly clever trick to shrink things down.
Have you ever noticed how some people can stay perfectly calm even when someone is shouting right in their face? They naturally absorb the tension in the room. Well, in the invisible world, a dielectric does exactly this. It's an insulating material that acts like a magic buffer, absorbing massive electrical tension without actually conducting the current itself. And this brilliantly illustrates how a dielectric works inside a capacitor. Just think of a capacitor as a sponge for electricity. A standard sponge can only hold so much water before it leaks everywhere. But if you put a dielectric, like plastic or glass, inside the capacitor, it's like giving that sponge much larger pores. It allows the component to hold massive amounts of charge without the voltage or the electrical pressure rising too high and dangerously leaking out into your devices. It's essentially bottling up a storm, keeping it perfectly contained until you actually need it.
And these little storage tanks are hiding absolutely everywhere. Mobile phones, ceiling fans, TVs, motherboards, chargers, cameras, the whole shebang.
Every time you flip on a ceiling fan and it starts spinning, it's a capacitor giving it that perfectly timed, massive kick of energy to get the motor turning. Inside your TV, they act kind of like shock absorbers, smoothing out the voltage so your picture doesn't flicker. Without capacitors, our modern electronics would literally just crash.
Physics in everyday life. Let's step out of the textbook for a second here. I want you to see how mastering this exact hidden capacity keeps our modern world moving safely.
Now, we're going to apply these calm, buffered concepts to highly explosive real-world vehicles where physics literally saves lives every single day. You've probably seen those heavy metal chains dragging behind petrol tankers on the highway and, I don't know, maybe thought a part was broken? But as the truck drives, air friction furiously rubs against the metal body, stripping away electrons. The truck becomes this massive charged conductor. If a single spark jumps from the truck to a person or a gas pump, the fumes explode. So that chain, it is quite literally a lifesaver. The really crucial point here is that by dragging a simple metal chain, the truck stays physically connected to the Earth. And in physics, the Earth is considered a perfect sink, with absolutely zero potential. Because of this constant connection, the truck prevents any dangerous charge buildup. All that excess electricity instantly flows down the chain right into the ground. No charge buildup means no sparks and absolutely no explosions.
The exact same terrifying buildup happens when a massive airplane lands at 250 kilometers per hour.
Remember the comb from the start of the explainer? That's simple static buildup. But scale that exact same physics up to a massive jet airplane flying through the sky, rubbing against ice and dust at hundreds of miles an hour. It builds up a terrifying amount of electrostatic potential. If it touched down on standard rubber tires, that huge electrical pressure would arc and blow the tires to absolute shreds. That's why aircraft tires are manufactured to be slightly conducting, so they can safely drain that charge straight into the runway.
The crucial takeaway here is that charge absolutely loves to move through conductors to find balance. And this behavior leads us to a fundamental, life-saving rule of physics. Inside a solid or hollow conductor, the electrostatic field is always exactly zero. Because the charges on a conductor rapidly distribute themselves on the outermost surface to get as far away from each other as possible, the entire interior is left completely free of electric fields. We call this electrostatic shielding. It's the exact reason why if your car is ever struck by lightning, the charge just flows right over the metal exterior, leaving you perfectly safe inside.
Now we reach the climax of our explainer. We've controlled electricity in trucks, planes, and buildings, but what about literally holding it in your hands? A medical defibrillator is essentially a massive, perfectly engineered capacitor. It executes 3 dramatic steps. First, it charges up, slowly collecting energy. Second, it holds that stored energy in a state of high electric potential. And third, the exact moment those paddles touch the chest, it discharges all that energy, calculated by the formidable formula U equals 1/2 CV squared, in a single intense millisecond.
So why does this matter so much? Well, because the human heart runs on tiny, delicate electrical signals. When someone goes into cardiac arrest, those signals are often just glitching out of rhythm. That massive, instantaneous burst of stored potential from the capacitor acts like a hard system reset, forcing the heart muscles to shock back into sync and restart their natural rhythm. It is raw, incredible physics bringing a human heart back to life.
Section 6, Summary and the Magic Revealed. Let's pull it all together now. Take a look at this summary table, mapping everything we've talked about through our electronic vision. The water tank represents the electric potential, creating pressure. The petrol chain is grounding, using the earth to naturally prevent explosions. The defibrillator is a massive capacitor releasing life-saving energy in a fraction of a second. And even the smartphone screen you might be holding right now relies on capacitance. Your finger literally acts as a conductor, changing the local electric field, which is exactly how the phone registers your touch. So, as we wrap up, I have a question for you. When you view these principles through your new electronic vision, does the connection between a dragging chain on a petrol truck and the potential inside a 9-volt battery make those dry mathematical formulas feel a bit more alive? The physics in your textbook isn't just theory, it's the everyday magic keeping our modern world spinning safely.